I'm co-hosting the seminar today with Professor CJ Taylor. As a quick reminder, the previous talks from every Friday in this semester can be found on the YouTube channel. If you're joining via Zoom, please type in your questions in the chat, and then one of the student panelists will read them out. Feel free to ask questions during the seminar. If you have a question and you're in the audience, just raise your hand and we'll bring the mic to you to ask questions. Okay. With that, I would like to introduce the two student panelists today. Dexter Ong, who is here. He is in his first year in the computer science program, and he works with me and Professor Vijay Kumar on visual perception with focus on outdoor flying. Our second student panelist today is Fernando Cladera. Fernando is in his third year in the computer science PhD program, and he works on robotic perception with a focus on event-based sensing and aerial autonomy with Professor Anish, CJ Taylor, and Vijay Kumar. With that, allow me to introduce the speaker today. We have Professor Vivienne from MIT, who is speaking for us. She's an associate professor in electrical engineering, computer science, and she works on computing systems that are energy efficient. And these systems have been tailored towards tasks in machine learning, computer vision, and robotics. She's famous for her work on video compression, autonomous navigation, Internet of Things also. And she's widely recognized for her work in these areas. My favorite paper of hers is where she co-designed the hardware and the software for achieving very low power performance for visual-inertial sensing. This work is both very famous and very widely recognized and awarded, including the AFSR and the DARPA Young Faculty Award, the Edgerton Faculty Award, and several faculty awards from Google, Qualcomm, and Facebook. This includes academic awards also of the around best papers. In 2018, she got the best student paper award at the Symposium for VLSI Circuits. In 2017, one of her papers got the CICC Outstanding Invited Paper Award. And in 2016, she got the IEEE Microtopics Award. Very excited for the talk, Vivienne. Please, this floor is all yours. Thank you.
Thank you so much for the intro, and thank you for having me here today. So I'm really excited to share with you a lot of the work that we've been doing in my group. Generally speaking, we focus on energy efficient computing. For today's talk, I'm going to talk about how we apply that specifically to autonomy and navigation. And this work is done in collaboration with many folks. Actually, I know that Luca was just at UPenn earlier this week giving a talk. So he was actively involved in the Navion work, which I'll talk about, along with all these other students. And then a lot of the work I should mention is also, in particular for the robotics focused application, is done with Surtesh Kerman. So in fact, let me advance the slides. I would say so we actually have a joint subgroup of students that we co-advise on this topic. So we have students who know hardware and students who know robotics, and we kind of work together at the intersection of that. So if you want to primarily focus on some of the robotics or autonomy-driven applications for the work I'm presenting today, I would encourage you to visit the Lean website. And then if you generally want to know about energy-efficient computing, then you can visit my own website as well, see@mit.edu. Okay, so let's get started. So I think generally speaking, when we think of autonomy, one of the big application spaces is things like autonomous vehicles, self-driving cars. We know, however, one of the challenges there is that these cars need to collect a huge amount of data to understand their surroundings. So, for example, you have cameras and radars on these vehicles that generate what is reported to be gigabytes of data every 30 seconds. So just to churn through that data, the computational complexity is very high. So relatively earliest prototypes would have these huge amount of compute on these vehicles, right? So it was reported in 2018 that some of these vehicles have over 2,000 watts of computing power, basically a huge number of CPUs and GPUs that sit on the vehicle. They generate a lot of heat, and sometimes so much heat that you need water cooling. I would say that, some of the platforms that are out there today are still very much like that when you're kind of prototyping, self-driving cars. The other thing that I wanted to alert us all to is when we think of the computer, these autonomous vehicles, if we think of many of them, the hope is for autonomous vehicles that there'll be wide adoption in the future. The amount of compute you would actually do on these autonomous vehicles as you scale it up is comparable to that of data centers today. And we all know these days there's been a huge amount of focus on considering basically the energy consumption and thus the carbon footprint of a lot of these data centers. And so, for example, Facebook has reported that their data, or Meta has reported that their data centers in terms of inferences run, trillions of inferences a day. At the same time, if you look through the lens of, self-autonomous vehicles, if you consider, let's say they have, 10 cameras running at 60 hertz, and to analyze the data, you're going to run, let's say, 10 different neural networks on them. For one autonomous vehicle driving for 1 hour, that would be 21 or 22 million inferences. And then, of course, if you scale that up to 1 billion vehicles, we have a little bit over than 1 billion vehicles in the world today. That ends up being something like 22 quadrillion inferences per hour, right? So, of course, these are just projections, or it's the main message here is, number one, as you scale up the number of devices out there, the compute cost, even though per vehicle or per robot it's low, if you scale it up, it becomes more significant. And this is compute that we wouldn't have normally been doing before. So this is going to be just additional energy that we need to use to drive or enable this functionality, and that can potentially translate to increased carbon footprint. So that's definitely something to consider even at the larger scale. Now, of course, if you consider on the smaller scale, if you go to the other extreme, if you look at, there's, a range of robots that basically it's not just compute, but there's actuation. And for these robots, if actuation is very cheap, so for example, you can imagine these blimps where, you're taking very little power to actually actuate. There's a whole range of, miniature aerial vehicles and so on. In those particular cases, you want to keep compute low because actuation is already quite low. So compute can become the dominant source of energy consumption and really limit, the duration of the robot itself. And so the challenge, of course, is that if we start looking at, performing some of these very important computational tasks that we need for autonomy and navigation, if we look at the hardware that exists out there today, they actually consume a lot more power than what we would typically want to budget for these smaller robots as well, or even something as simple as something that would fit on something that can fit on your palm of your hand, like a phone, right? So as I mentioned, this also applies to applications beyond robotics. So for example, if you want to have compute on your cell phone, typically something like that, you would be limited in terms of power consumption to be below a watt. And the reason for that is that, on your phone, for instance, you can't afford to have a fan to cool it down. You need to have a heat sink, and the only amount of heat it can remove is up to a watt of power. So it's really tight there. And then, of course, you can imagine even beyond that for wearable things like, AR, VR, or, like your watch and so on, the power consumption there is going to be even lower than that because it's always, touching your skin. So you're going to be much more sensitive to heat. So the main message here is the power envelope, or the amount of power consumption you can tolerate for many of these devices, much lower than what the platforms can support these days. So for existing, even embedded platforms are over 10 watts. We know some of these embedded GPUs are 10 watts of power. And of course, also in a lot of these devices, if they're battery operated, the amount of energy that you have is quite limited on these devices because of the size, weight, and the cost of device. And so, consuming too much power means that you're going to be really shortening the battery life or the duration of the device itself. Okay. And so in the past, there have been, we've been very lucky in terms of how we've addressed this issue. Basically, we had things like Moore's law and Dennard scaling that gave us faster, smaller, and more efficient transistors, right? So that has driven us for the past few decades. However, there's a limit to everything. We know that has been slowing down over the past decade or so. Obviously, there's a limit in terms of, it becomes much more difficult and costly to make things smaller and more efficient. There's kind of a limit that you hit. And of course, people are working on that, but nonetheless, it's slowing down. So we just can't rely on, more efficient transistors to give us this improvement in speed and efficiency that we need. So instead, what we really need to do is we need to design specialized hardware for specific applications to give us this improvement in speed and efficiency, right? So rather than having general purpose a CPU for all of these, can we really tailor the hardware for these particular applications? And that tends to allow us to improve efficiency and speed. And really what we need to do is think of basically redesigning all the computers from the ground up. Okay, so it opens up this big wide opportunity of what can we actually do. And so again, taking a step back within our group, that's what we want to do. We want to think cross-layer design, right? So we start by first thinking about the algorithms themselves, for example, looking at deep neural networks these days. In addition to trying to achieve a certain accuracy or quality of result, can we also optimize for energy consumption and things like latency and speed? Then can we design new hardware architectures that exploit certain features of the algorithm so that we can run it more efficiently and run faster. Typically, and you'll see the theme of this is that we're trying to think about the way in which the algorithm uses data. Data is going to be a dominant consumption, dominant thing that limits both energy consumption and speed. So we need to try and come up with new computer architectures that are specialized to the needs of this given algorithm and then manage that appropriately. Then we realize these architectures in actual chips or circuits that we build. And then we also want to integrate into actual systems so that the ultimate goal is to consider the interplay between the compute, the actuation, and the sensing. So overall, we want our overall system to be energy efficient. Okay, so I already kind of get a little bit of a hint. So where does the energy go? If you're going to redesign everything to make things energy efficient, your first question should be, well, what consumes the energy, right? So as it turns out, energy is dominated by data movement. It's not actually the computations, the data movement. So for example, if we look at this slide, we're showing here the energy costs for various different types of computations operations, so multiplications and additions at different precisions. So you can have 32-bit floating point or 32-bit fixed or 8-bit fixed integer. And you can see obviously so first of all, multiplications consume more energy than additions. And then as you scale down the number of bits for the multiplier, the energy also reduces. What's interesting though is if we start looking at, well, that's the multiplication itself, but how much energy does it take to deliver the inputs to that multiplier from memory and also write back the results to memory? And so if you look at a very small memory that's on your computer chip, so let's say 8 kilobytes of memory, not very much, reading 32 bits from that on chip, already very close by SRAM, is going to be more energy than doing the multiplication on that piece of data itself. And then even more, as you increase the size of the memory and as the memory goes further away from where the compute is happening. So for instance, often we have memory that's off chip in DRAM. That's going to be even more expensive because you have to move the data further, right? So you're looking here, for example, DRAM, you're talking about an orders of magnitude higher energy cost to move a 32-bit value from DRAM than it is to perform a multiplication on it, right? So really, if we want to design systems that are energy efficient, and this is also something that limits speed as well, often to deliver the data, we really need to address this, data or memory bottleneck and address the data movement. Now, the challenge is if we turn towards looking at, tasks in autonomy and navigation, they tend to use a lot of data, as you all must know. So for example, if we think of things like trying to do a semantic understanding and labeling, for example, pixels in a given frame, first of all, you often want to have high frame rates because you want to, be able to sample, especially if you're moving quickly, you want to be able to sample your environment quickly so you can react to anything that's changing. You want to often have large resolutions because you want to, let's say, see things that are very far away. And so you want to have more pixels to represent these smaller objects that are at a distance. And then often you might need to resolve things at, resolve things at, different resolutions. So detect people at different scales. A popular approach of this is doing things like building a pyramid. So then you need to expand the data, and that could be another order of magnitude or two. Right? Or it could be using neural nets, which we'll talk about, which again expands it in a different way. So nonetheless, it's a huge amount of data you need to process. Similarly, as you're doing the navigation, you might be building a map to get some kind of geometric understanding. And you know that as you navigate longer, the size of the map is going to grow, and then you have to, somehow deal with it. So one of the kind of first works that we tried to do to kind of investigate how to deal with these challenges in the context of autonomy of navigation is look at visual inertial localization, right? So we all know that, one of the first key things you have to do for autonomous navigation is figure out where you are, your location, and where you're actually looking. And a very popular way of doing this is to like mount using a camera and an IMU mounted on the robot, and then fuse the two to answer this. And of course, we know we can also use this for augmented reality and virtual reality. So I think with you guys, I don't need to explain too much, but you can see like it comes in and you have this robot, you're trying to figure out where it is in the 3D space. So one of the first projects that I did with Surtesh, and also Luca Carloni was also involved in this when he was a postdoc, was to see if we can do localization at extremely low power. So in particular, we want to see if we can do localization in the milliwatts, and we showed that we were able to do it in under 25 milliwatts. And this is so this is a chip that we call Navion. It's the first chip that performs complete visual inertial odometry. I won't go into too much of the details because last time I gave a talk in 2019, we went through it, but I'll just give you the highlights. So the highlights are as follows. So what can it actually achieve? So on the front end, it's doing with the camera data, is doing feature detection, tracking, and outlier elimination. And for the IMU, we're basically doing pre-integration of the accelerometer and gyroscope data. And then we're also including the backend where we're doing postgraph and optimization for the postgraph itself, so that the whole thing is integrated on chip. So here's a picture of a dye photo of the chip itself, and you can see the scale relative to the size of a quarter. It's 4 millimeters by 5 millimeters. And we compare the energy consumption to what you would consume with a mobile or desktop GPU. It gives you orders of magnitude reduction in energy consumption. The other thing I just want to highlight is, as we mentioned, so it's running at under 25 milliwatts, let's say 24 milliwatts. Often when people run or things run at very low, power, the question is, well, is it still going very quickly? So yes, indeed, it is going quickly. So it can consume from a camera rate, from like the input camera, it can process video at 28 to 171 frames per second. So it still is not giving up any speed for this energy efficiency. And then the key insight, or the key thing that I want you to notice, is from a memory point of view, it's consuming very little memory. So it's under a megabyte of memory, right? And so that was one of the key things so how do we actually do this? And again, the key thing is to reduce the data size. So two things. So one is, first of all, we want to integrate all the computation on chip, right? So as I mentioned before, if you go off chip to DRAM, it's going to be very energy costly. So all the processing is placed on chip. If you're going to put everything on chip, you also need to keep the memory small, just for both cost reason, and also accessing data from a smaller memory is going to be much more efficient than a larger memory. So we have two, from a high level, explain the two strategies that we do that. One is in terms of the frames that we need to use on the front end for do things like tracking and the stereo computation. We apply low-cost compression to these frames. So what's really critical here is you don't want to do with some super fancy, H.264, HEVC type of compression on this, because then the cost of compression is going to exceed the benefits of the compression itself. So some very lightweight compression that we're doing here. Basically, what we do is we divide it up into a grid, and for each box of pixels, we kind of cap the min and max, and we kind of adaptively quantize each of these 4x4 blocks of pixels. And then on the back end, because we're dealing with a graph processing, we know that there's going to be a huge amount of sparsity there. So then we have hardware that can also exploit the sparsity of the back end. And that allows us to significantly, not just reduce the computation, but most importantly, reduce the storage cost as well. So by doing this, we're able to reduce the overall storage or memory that we have on chip to under a megabyte. And that allows us to achieve the energy efficiency. So, once you're localized, another very key important thing that you want to do is to understand your environment, right? So, typical types of things you're trying to do are, given an image, can you estimate the depth of how far away things are? Or as we mentioned, given an image, can you label semantically what all the pixel values are? Now, again, it's no surprise to all of you that, these days, the state-of-the-art approaches to do a lot of these things is to use neural networks. Now, the challenge here is if you think about the computational cost of these neural networks, they often require several hundreds of millions, or in these days, billions actually, of operations and ways to do the computation. And if you compare it to something that we use every day that's on our phones all the time that we're using right now, let's say video compression, which is very ubiquitous, it would be like over 2 orders of magnitude more complex, right? So one of the ultimate, visions would be, can we make something like neural network, like deep learning, to be as ubiquitous as video coding, so that we can do it with all cameras and all devices, and they can actually extract and tell us meaningful information. But clearly, to enable that, we need to overcome this huge computational complexity hurdle. And of course, we know that neural nets are used beyond just visual understanding, but for a wide range of applications. So it's ever more important to make it ubiquitous and so also accessible to folks. Okay, so let's think about what are the opportunities to make the processing of deep neural networks more efficient. So one very strong, attribute of a neural network, which is great, is that there's a lot of parallel operations. This is why it runs beautifully on a GPU. So high throughput is possible, okay? But the challenge, and this is faced with GPUs and all other type of processing, is going to be the memory access bottleneck. So if we think about it, for every multiply and accumulate, which is one of the key operations in a neural network, for each multiply and accumulate, which we'll call a MAC, it requires 3 memory reads, right? So you need to read the filter weight, the feature map activation, or input pixel if you're in the first layer, and then also the partial sum, because you're doing accumulation, and then you're going to write the partial sum back to memory. So right off the bat, that's a 4-to-1 ratio in terms of memory access versus compute. Secondly, if we think about the energy cost of compute versus memory access, in the worst case scenario, and we would never do this, I'll show you ways that we're going to get around doing this, but if you were to read that data from the DRAM, that would be 200x higher energy per read, and you have 3 reads, than each multiply and accumulate. And then you have to spend another, 300x to write it back to the DRAM. So for something like, any neural network, let's say if you had AlexNet that had 700 million max, it becomes 3 billion DRAM accesses. So again, the main message here is that we really need to deal with this memory bottleneck. And this is one of the challenges. And, these days there's going to be, I'm sure you've all seen many different, specialized hardware for DNNs. This is one of the key challenges that they're dealing with, right? So what can we actually do to address this? Well, another nice feature for deep neural networks is there's a lot of opportunities for what we call input data reuse, meaning if you read data in, you're going to reuse it for many different operations, right? So for example, if we're talking about convolutional neural networks, which we typically use for images, that you can actually, you have a filter that kind of, performs convolution of the input. So the same input activations and weights are going to be used multiple times, just in different combinations through that sliding window approach. We often need to apply multiple filters to the same input to generate multiple output channels. So that means any input value or input activation is going to be reused multiple times across the different filters. And then finally, if you use a batch size that's larger than 1, that means that at any given filter weight that you read onto the chip can then be applied to multiple inputs, right? So you're reusing the weight to multiple inputs. This might give a hint to some of you as to why, if you have a larger batch size, things tend to achieve higher throughput on a given processor. It's because of this reuse opportunity. Okay, so from a hardware standpoint, how can we exploit this, right? So what we want to do is typically for some of these processors, we're going to have an array of what we call processing elements. And each of these processing elements will be able to support a multiply and accumulate, because that's the key operation. What we would also like to do is insert a small memory in this processing element. By small, I mean ideally very small, like let's say under a kilobyte. So it's super cheap to read from, right? And so it's very low cost. And so you can imagine having a small memory that's, half a kilobyte or kilobyte is going to be around the same energy that it takes to do that multiply and accumulate. As I mentioned, you can have an array of these process elements to run in parallel, but what you'd like to do is be able to allow these processing elements to talk to each other and share data. So you just have some form of network on chip. And then to communicate across the processing elements, it's going to be a little bit more expensive than reading from the small memory, maybe 2x. And then they might have a larger shared memory buffer across all of them. We call the global buffer. Reading from that's going to be maybe more expensive, 6x. And then most expensive would be going to DRAM, kind of 200x. And you can store the most data there, but it's very expensive. So the key challenge here is that what we want to do is we want to take this very large neural network. You want to break it up to small chunks that will fit into this very small register file of 1 kilobyte. And then what you want to do is think of what is the order by which I want to move this data through this memory, what we call the memory hierarchy, so that by the time it gets to this register file, I'm going to be able to use it for as many operations as possible, given that one transaction for it to get there, right? And so that's kind of the key challenge here. The analogy for those of you who might not be familiar with hardware would be like, let's say you are, you could store a lot of data at home. You go to work, you want to think, well, I only have a small bag with me to go to work today. What can I fit in that bag to make it most efficient? So it's very easy for me to access it and get the most work done, but I can't fit everything there today. Maybe you have a lab mate who also has a bag, so that would be another processing element. So you can maybe exchange from them. Maybe, you could store a little bit more in your office, but it's like takes time to walk to the office. That would be your global buffer. And the worst case scenario is to go back all the way home on this huge kind of thing. So you kind of do these optimizations yourself these days when you're doing this. But nonetheless, that's the challenge that we have from a hardware standpoint. And so the order in which you process these chunks, we call that a data flow. So one of our works on this early on was kind of really focusing on optimizing this, having this energy efficient data flow. And this allowed us to process these deep neural networks in under 1/3 of a watt. One of the first chips that showcased this kind of approach, also with a lot of flexibility, is the Iris chip. This was designed in collaboration with Joel Emmer, also at MIT. And so we had this, array of 168 processing elements with this shared buffer of 100 kilobytes. And here's the chip itself. And so with this really efficient data flow that exploit a lot of data reuse, we were able to reduce how often we access this global buffer by 100x, and then also how much we access data from off-chip by over 1,000x. Okay. And so as a result, by doing this, you get an order of magnitude energy reduction compared to a mobile GPU. Okay, so that's the high level data. Of course, there's been a lot more work in this space as well. Again, really trying to focus on reducing data reuse. And we've had some other work also focusing on doing things like exploiting sparsity. So if you have a 0, how do you can skip, actually, the first version of Iris does part of this, but also, can you skip the 0 operation to save energy and speed? Can you compress the data? And so this is a thriving area of research as well in the computer architecture community. And of course, we already kind of alluded to sparsity is important, even in the Navion chip in the back end with that factor graph. How do you design hardware to exploit that? Okay, so this is great from a hardware standpoint. But if we take a step back, there's still obviously some challenges that we face. What we really care about is the trade-off between energy and accuracy. We still have some issues, right? So if you go all the way back, I guess this is now more of a decade ago, the pre-return of neural networks, what was considered state-of-the-art at that time was doing histogram of oriented gradients, right, in a deformable parts model. So if you looked at the energy cost to build hardware for that, and we did do that, it's actually under a nanojoule per pixel, which is really great. That's actually just as good or even better than video compression, which is quite impressive. But of course, the accuracy there is not what we really want. And so obviously there was this, resurgence of DNNs, very exciting. You get, 2-3x improvement accuracy, and even beyond that, this is quite old. But the challenge, of course, there is that the energy costs went up, right? So this is the x-axis here is linear scale, but then the y-axis is exponential scale. So like if you were to ask someone, I'm going to double your accuracy, but I'm going to charge you, over 100x at higher energy, meaning your, phone would die 100 times faster. I don't think anybody in this room would be very excited about that kind of a feature, right? So really, we need to account both for accuracy, energy, and hardware by itself might not be sufficient to do that. We have to start thinking about the algorithms as well. And so again, there's been a huge amount of activity in this space, like really focusing on how do you enable energy efficient processing of DNNs, both at the hardware level and at the energy level. And so in our group, this was A couple of years ago, we did a lot of surveys and tutorials on this topic. And what was really evident from the body of work out there was that there's limitations in some of the existing approaches. In particular, what I want to highlight is on the design of efficient deep neural network algorithms, right? So even to this day, with a lot of work out there, you can classify the approaches of designing efficient DNNs into 3 categories. One is what we call network. Everybody calls network pruning. The idea there is that you set some of the weights in your neural network to 0. And then, of course, what you need hardware to be able to exploit that, right? You need to be able to turn those zeros into savings in terms of energy and speed. Another is to come up with new DNN models or network architecture. So for things like, MobileNet, you decompose your, regular convolution into depth-wise and point-wise convolutions and stuff. Those kind of techniques that people play. And then also, of course, reduce precision, right? So rather than 32-bit floating point, people have been looking at, reducing down to 8-bit integer, which is pretty widely used now. And then, of course, even more extreme, there's sometimes they can go all the way down to binary. Now, a lot of this work tends to focus on reducing the number of max, so number of multiply and accumulate operations, and number of weights. But what we actually care about from a systems point of view, eventually when you're building it or like running it, what you care is, am I saving energy? Am I reducing latency, right? And so as it turns out, by looking at just number of max and weights, those are actually not good proxies for these system level metrics that we care about. So for instance, if we look at this plot over here on the left-hand side, this is from Google's mobile vision team. And what they showed is the number of max versus latency on the y-axis. And what you can see is for a given number of operations, there can be a 2x swing in terms of the latency. And then for a given latency, you can see a 3x swing in terms of number of multiplies and accumulates. Right. So obviously it's not, just looking at the number of operations itself is not a good predictor of the latency. Similarly, in some of our own works, we've noticed that the weights alone are not a good metric for energy consumption. Why? Because weights are not the only thing that's causing data movement. You also have to consider your input and output feature maps, right? Those also can move around a lot in your system and then cause a lot of energy consumption. So shown here, we're just showing an energy breakdown of GoogleNet, but the intuition behind that is that we're dealing with more than just weights, right? So just because you have a small neural networks in terms of number of weights doesn't necessarily mean it's going to be energy efficient, because you have to store and move other types of data. And so what we're advocating for at a high level, the high level message is we need to somehow think of ways to insert energy and latency or whatever system metrics you care about into the optimization and design of the DNN model itself. So one of the kind of first approaches that we looked at was this approach called energy-aware pruning. And the idea here was that rather than removing weights that are small, we should also factor the energy consumption of those particular weights and the impact of that weight on energy consumption, meaning its impact on feature maps and so on, into the removal of that weight. So one strategy that we took in this particular work was that we sorted the layers from highest energy to lowest energy and then pruned the high energy layers first. And the idea being that, it's kind of get diminishing returns. If we prune the high energy layers first, hopefully the weights that we remove are going to be very energy costly. And so by doing this, we're actually able to reduce the energy consumption much more relative to just using magnitude-based pruning, which again is just removing the small weight. So while magnitude-based pruning gives you 2x savings while maintaining the same accuracy in terms of energy, using energy-aware pruning gives you 3.7x savings. The main, this is one approach to do it. The high-level message is that if you care about energy, then you should try your best to directly target that in your design process of the DNN itself. Another piece of work that we did, this is in collaboration with Google's mobile vision team, was they had a question after seeing the energy aware paper, was whether we can automate this more for any given platform. Okay, so this work is called basically NetAdapt. And basically the idea here is that you're taking empirical measurements from a given mobile platform of latency, energy, or whatever system metrics you want, and you're going to keep it in the loop and automatically adapt your neural network to that given platform. So the ideas here is as follows. You start out with already some kind of pre-trained neural network. You're going to measure the performance of, the different layers of basically of that neural network on that given platform, right? And then you're going to use that to iteratively help you make decisions in terms of how you might modify that particular, the architecture of that particular network to achieve the accuracy and the latency that you care about, right? So in this particular approach, it used an iterative approach where basically for every layer, like it would generate a bunch of proposals where for each layer you would reduce the number of channels till you hit a certain latency budget. And then you would train up those proposals, pick the one with the highest accuracy, and then you would start again. And so iteratively, you'd be shrinking for, a given latency, you would be shrinking your network. And you would know that the network that you get out of this is going to hit that latency target that you care about. And then with these different proposals, you're trying to find the one that gives you the highest accuracy. And the nice thing about this is that because you have the hardware in the loop, like you're empirically measuring it, you don't have to do any modeling of the compiler stack and the underlying architecture. The high level thing is just putting the hardware in the loop to make this design. A nice thing about this approach also is that there's very few hyperparameters to tune. Basically, you just need to say for each iteration, how much do I want to shrink the latency by? And by doing this, you get, a 1.7x speed up, but even a very small network like MobileNet for similar accuracy compared to other techniques. And so the code for this is all available on the NetAdapt website. So this was all done on image classification, which I would say at the time, that's, even to this day, a lot of the experiments are done on image classification. But obviously what we also care about is thinking, using neural nets in a different manner. For example, using things like monocular depth estimation, where given an RGB image, can you predict the depth of each of those pixels? And the output is actually a dense output as opposed to an image classification where your output is just a label of a given class, right? And so, one question was whether or not when you have a dense output, can you still apply a lot of these techniques that we're looking at? Because you can imagine it's much easier to shrink a network down when the output is very sparse. But if it needs to maintain a lot of information, it might be much more difficult to make it dense. So we did, in fact, apply NetAdapt to this depth estimation technique. We also did things like do depth-wise decomposition of the decoding layers as well. And so as a result, by doing this, the conclusion is, yes, indeed, you can maintain high accuracy while having high throughput. So this is some performance on a Jetson TX2 GPU. So to the right-hand side is better, and on the x-axis is going to be the delta 1 accuracy. So the number of pixels that are within 25% of the correct depth. And then you can see that, by applying all these different efficient network design techniques on fast depth, you can get, 10x, an order of magnitude speed up, over an order of magnitude speed up for the same accuracy. And then this was presented at ICRA back in 2019, and we actually, caught some live footage on an iPhone with it. You can run it on your iPhone at 40 frames per second. Okay, so this is primarily how to make the network efficient. There's one other thing that you should also consider when we're trying to make these neural networks efficient, and that is the actual, what one would call like the neural architecture search process, right? So we showed the NetAdapt, the first version, we're just shrinking the channels for a given layer, and then you have like a bunch of proposals, you select one of them. But this is still a very iterative approach. Can you speed that up itself? Even though you need to only do this once, it still can be very computationally intensive. And so actually there's been a huge amount of work in this space as well. Typically there's 3 components that you should care about for neural architecture search, or 3 things that contribute to the speed. One is to train basically a super network, which basically has all these possible neural networks embedded in this very large network. So it's kind of defining the search space of the neural network. So how do you train that up? Because of course you need to set the weights to something. Then there's the next step is often then within the search space, you have to sample, you select certain, architectures that you want to try out, and then you need to evaluate them, which often means you then need to, train them a little bit more so that you can compare them. And finally, when you pick, what you think is the one that you want, you need to do a lot of fine tuning and further push the accuracy, right? Because during the sample and evaluate, all you really need to do is like, when you're looking at different networks, you just need to compare them, like which one's doing better than the other. Okay, so there's been a huge amount of work in this space. And so, the approach that we took was kind of an extension of NetAdapt v2. So we had various things that we did to try and speed it up. So first thing is, when you're training that search space itself, it would be great to be able to train multiple neural networks in a single forward pass, so you can reduce the time you spend on training the whole super network. As we mentioned in NetAdapt, originally, you're only searching the number of channels for a given layer, but it's also important to think of not just the width of the layer, but how many layers you have. And so, of course, you can imagine that allows us to search a much wider space, but it can be also quite complex. So there's a way that you can kind of merge the depth information with the width information to one dimension, and that allows you to speed up kind of the search and evaluation. So step 2. And then finally, when you're trying to pick which one you want, we also do what we call multi-layer coordinate descent optimization. So you basically consider the joint effects of multiple layers when you're doing the evaluation. Another really important thing here is that as we mentioned, we want to use real metrics like latency, like real system metrics like latency in the design or in the evaluation. But of course, those are not differentiable. So you also need a technique there that can support that. And so with the combination of all of these, we're able to really speed up the neural architecture search to almost 6x. And in this graph, you're looking at the resulting network that you found. So latency on the x-axis and accuracy on the y-axis. So you can see that this work provides you with kind of at the upper left-hand corner is the best, better, basically lower latency, higher accuracy. And then the size of the circle tells you how much search hours of doing the actual search to find that it is, and it's quite low. Okay. So, but like, again, the high level thing here is that you don't not just want to make the neural network that you find efficient, you want to make the search process also efficient as well. Okay, so one thing that we also start to think about is once you have this neural network for, let's say, depth estimation, you actually want to use it in practice, not just like in terms of running it on a data set, but in like if you actually apply it somewhere, can you use this information that's provided by this DNN depth prediction to make a decision of, let's say, navigating and so on. And what's really lacking when you think about using a DNN as some form of a sensor is, unlike a typical depth sensor, you don't have a sensor noise model. So how kind of confident are you in terms of the depth that it's measured, right? So let's say you're taking an RGB image here, you run a DNN, a monocular depth estimation on it here. So this is the depth itself. So I believe lighter is further, and this is the actual ground truth. So if you had the ground truth, you could see that there's a lot of error near this image here. And that makes sense because sometimes it's like the image also has perspective. And so since we're just doing kind of RGB and trying to do monocular depth estimation, there could be a lot of error in this, right? They can't tell if it's actually far or not. But in practice, we actually don't have ground truth, obviously. And so the question is, can you run some kind of uncertainty metric on the DNN itself to also estimate, what parts, you may say that these are all the depths that are, how certain are you? And hopefully the certainty aligns with the, or high uncertainty aligns with high error, right? So like, oh, maybe we shouldn't trust these results that much. And so this would be the ideal thing that you would see. And so you would see like, oh, where the image is, where you have high errors, also where you have high uncertainty. So this is an area, again, that folks have been looking at for a while. And a typical approach to do this, or a very popular approach, is to use an ensemble. So you train multiple DNNs on the same task. They were initialized with different weights. They might have different architectures and so on. And then through this ensemble, you check the agreement across the different DNNs, right? Of course, the consequence here is that you're running multiple DNNs on the same input. So said running, one DNN on an input is orders of magnitude higher than something like video compression. Now you're talking about running multiple DNNs, and multiple can be, 8, 10, significant, like order of magnitude, right? So what can we do here to address this? So some of the recent work that we do is looking at, inspired by the concept of kind of structured for motion, you can think of uncertainty for motion. So particularly in the context of robotics, typically it's not like a different images. You get a video stream of images that's coming in. So then there's going to be a correlation between some kind of temporal correlation across the different frames. So can we actually exploit that? So basically, you run the DNN on one frame, and then you run a DNN on the other frame, and you figure out the correspondences between frame 1 and frame 2. and then using those, the corresponding results, then you end up having multiple depth estimates for that same pixel. So as a result, you're only running 1 DNN per input, as opposed to, let's say, 10 DNNs per input itself. Now, of course, the overhead here is that you need to compute the correspondence itself. And so as long as you can keep that computing the correspondence cheap, and right now still DNNs are quite heavy, you can get some benefits. So for example, in this particular paper, we looked at FC DenseNet, and if we're doing an ensemble of 10, so in theory, the baseline is running 10 DNNs per image to get that uncertainty metric. If we're able to find this correspondence in real time, what we can do is achieve almost a 9x reduction in energy and a 6x speed up on an NVIDIA RTX GPU. And so, of course, the reason why it's not 10x is because there is that overhead of viewing the projection and finding the correspondence. Another thing that we often care about is, building a map of the environment. We alluded that to before. And a very typical kind of representation that you want to have of the map to make it very compact is, for example, using Gaussian mixture models, right? So you can construct a really compact 3D map of the environment, which is great. One of the, key steps in doing that is, first, when you get a 2D depth image, you need to break it into a bunch of GMMs, right? And so then you can have significant reductions. And so there's been, again, a lot of work looking at doing this. How do you take a 2D dense image and generate a GMM representation? I think what's interesting is the focus in the previous work has primarily been reduce the final representation. But the key thing to also think about is that while you're generating that representation, while you're generating the GMM part, during the compute of that, you're also generating a lot of data movement. So the compute cost, there's a lot of memory that's going on as well, right? And so that can be memory costly. Even though your final result is very compact, the process of generating that final result can be very computationally expensive due to the amount of data that you're generating. So some of the work that we recently did was try to focus on making that process of computing the GMM to be very efficient as well. And so we call this approach the single pass Gaussian fitting. And so there's two key things. So one is, in the depth image itself, we break it up into rows. So basically the scan lines, we segment it into, so we just process row by row. So this allows us to only store kind of a row of data at a time as we're doing the computation. It also makes some of the computation more efficient. And then once it segments it, then we make the decision of which rows which segmented parts of each scan line to fuse on a row by row basis as well, right? And so the reason why this actually reduces the amount of memory that you need to use, both in terms of storage and memory access, is that, first of all, it's single pass. So you only do one pass. So rather than, taking an image and iterating over and over and over again, which means you have to store a lot of data and iterate, we only do it in a single pass. And second, by doing row by row, it allows for the inference pass to be quite efficient in a single pass as well. So how does this compare to other approaches? So if we look at its performance on the TUM data set, looking at, if the map is similar accuracy and similar compactness, we compare it to hierarchical E&M, normal distance transform, and the growing region approach. You can see that in terms of using SPGF, the amount of memory overhead that you have is significantly lower. So if you use, let's say you use one core for each of these, you have almost 50x reduction in the amount of memory. If you want to use multi-core, so then you need to share more, you have their own memory that you need to store and stuff, it'd still be an order of magnitude less memory than prior approaches. So they're previously in the megabytes, now we're talking about kilobytes. And then, so what does this translate into to the metrics that we actually care about? Because memory is a way to estimate things like energy and latency. So from a latency or basically throughput point of view, you can see that the SPGF gives up to 5x speed up, or 40% speed up compared to something that's very efficient like NDT, and 5x speed up because it can very easily parallelize. You can imagine with all of those different rows. Then, and from an energy consumption point of view, it also gets energy savings about 3x, right? So the key thing here is that you're only using kilobytes of memory overhead, and you can do real-time processing even on a very low power ARM Cortex CPU. Okay, so the last thing I kind of wanted to talk about, second last thing I want to talk about is some of the work that we've also been doing on mutual information based exploration. Again, for those of you not familiar, is you know, when you're doing exploration, what you want to do is try and figure out where you should go next to gather the most amount of new information compared to what you already know. So a typical thing would be, you know, you have this occupancy map, you're trying to decide where to actually scan. You would compute the mutual information of this map, and that would tell you, you know, where you should go to get the most information. You would go there and you would actually scan it. Okay, maybe in the interest of time, I'll skip it, but basically the key idea here is that you have, you know, the entropy of your current map, you compute the mutual information, you figure out where to go that can reduce the amount of entropy in your, reduce the amount of uncertainty in your map itself, right? I'll be a little bit quick here because I talked about this last time I was here at GRASP, which is basically, okay, so it's well known that if you use Shannon's mutual information, you have very theoretical guarantees to make sure that you can actually fully explore your given space. The one challenge in that computation is that you have this like expensive numerical integration that is proportional to the resolution. So the computation there can be quite high. So the key insight for fast Shannon mutual information, or FSMI, is that actually if I compute the MI for all the cells in the entire array together at the same time, a lot of, you can use that to basically avoid this expensive numerical integration. You can get rid of the factor that's related to the resolution at which you're integrating on, right? And then of course you can further speed this up, like this ON squared becomes ON if you kind of also truncate the Gaussian itself. And this is actually also done in the CSQMI work that has also been done at UPenn. So when you compare all of these, the original MI versus FSMI, CSQMI, and the approximate FSMI with the truncated Gaussians, you get much more of a linear factor. And so if you measure this on just running it on a regular CPU, you get significant speed ups. And even on an embedded CPU, you also get significant speed ups in terms of, this is measured in terms of the latency, so lower is better. Okay, so that's some of the prior work, and this is just a demo of showing like a small miniature car in a mocap room for localization and trying to go to the location where it has, high mutual information. Okay, but what's interesting here, so even if you do all that with the algorithm, the hardware itself becomes a challenge. So in theory, looking at the, the formulation, like the computation that you do, it should be embarrassingly parallel, just like DNNs. There's like a lot of things that happen in parallel. It should run really fast on multiple cores, right? That should not be an issue. The issue, you should not be surprised, it repeats over and over again, is that basically what you need to do, so you could run, for example, all the different rays that you're sending out, the depth rays, you can run those all in parallel, but they would all need inputs from something that's storing your occupancy map. And then once you've computed the mutual information on all these rays, you can sum them up for the mutual information at that location. The issue is accessing the input data from this occupancy map. So what we know, again, in hardware is the power consumption of the memory scales with the number of access ports that it has. So typically, in most SRAMs, you would limit the number of ports, basically the number of things that you can access independently from memory to 2. So you can access from 2 different addresses of the memory at a given time, okay? But of course, if you have, an occupant, if you only can access 2 things at a time, but you have many cores, you can imagine you're not going to be able to sufficiently deliver the data from your occupancy map storage to all these different cores. And you might need to have some arbiter in between to try and keep these different cores busy, but fundamentally there's a bandwidth limitation here, right? You just can't deliver enough data. So what you're limited by is, again, the data delivery itself, not the fact that you can compute all of these in parallel. You just can't get the data to your core for them to run in parallel. So the design question is, how can we better design the memory to address this? So first of all, what you can do is you can break up this very large memory into smaller memories, right? And each of them will store a different part of the occupancy map. That's great, but then the next question is, well, what part of the map should be stored where? Right? Because once you store it, it's not like you can keep on changing it. It's going to cost you to change it. You need to store it somewhere. And so what you want to do is that as you're processing these rays, you want them to not conflict, meaning that you don't want them to be accessing the same memory bank more than 2 times in 2 different locations. right? So what we notice is the access pattern, looking at, one quadrant is, and at this 0 point, these rays in different colors are emanating out, and then the number here reflects like what cycle it's accessing on. So any given block with the same number means that at the same time, those blocks in the occupancy maps are being accessed. And so then the question is, given that we know this pattern, how should we break up this occupancy map into different, kind of sub memories or sub banks? And so what we're showing here on the right-hand side is the color indicates which bank it is. And so what turns out is that diagonal pattern works very well here, in the sense that for any given diagonal in a different color, you can see that the same number doesn't appear more than twice. It only appears twice, which means I'm accessing that particular memory bank, only 2 values from that particular memory bank at that given time. Okay. And so with this very customized kind of banking pattern that we selected for the memory, we're able to achieve significant throughput performances because of the parallelism. So how good is it? That's what we should compare to. So, in the ideal situation, if you were not limited by memory, let's say you had infinite memory bandwidth, you could always access whatever you needed. That's what's shown here in the black dotted line. And then using the techniques that we had, so with the diagonal banking, we also do some other things where we're packing multiple values into each address of the memory. You can achieve within 6% of that theoretical limit, right? So I've just to read this graph here, this is the throughput on the y-axis and the number of cores on the x-axis. So you would expect as you increase the cores, the throughput would increase. But if you, for example, only had, if you pick the wrong bank, if you had a vertical, like just one bank, you can see here in the blue, like nothing would happen because you can't even deliver the data to it doesn't matter how many cores you have, you can't deliver data to them. If you pick the wrong banking pattern shown here in the red, right, it would eventually flatten out, right? But then as you pick the diagonal banking pattern with some packing, you can actually get very high improvement. And so basically what we're able to do here is to compute an entire map of 200 by 200 meters with 0.1. So 200 by 200 quadrant, like occupancy map, you can do in under 1 second and under 2 watts on an FPGA, right? And so that's, of course, much more efficient than a CPU. But the high level message I want to emphasize here is that you've designed the memory very specific to your access pattern. Then actually another iteration of this that happened was one of our students was thinking, well, it's one thing to say you can compute all the mutual informations that are given, all the cells on a given rate. What if you just say, well, why not try and compute the mutual information of the entire map at the same time? So as it turns out, what that allows you to do is that, let's say you're looking at 2 different positions, but the rays would intersect with the occupancy maps similarly at the same time. So if you're computing the mutual information for all the positions of the map at the same time, this allows you to kind of reuse a lot of the computation that you're doing for the different ray intersections. So you can compute it once and then use it for many positions on the map itself. And so as a result, and from a complexity point of view, rather than being proportional to the cells per ray, number of rays, and the size of map, now you've kind of dropped, you're no longer dependent on the cells per ray. So this actually gives you an order of magnitude speed up over FSMI itself. Again, kind of rethinking from compute and computational standpoint, you can get these savings, right? So this whole body of work, which is basically, I would say, a series of 4 papers. So we start with an algorithm optimization, so computing the MI for every cell. You remove the numerical integration, gives you several orders of savings. Then you design that hardware that we talked about with optimized banking pattern, gives you another order of magnitude savings. You can actually reformulate it with the FCMI. So the C stands for continuous because you actually have to do a continuous representation of it to reveal this type of recursive structure. That allows you to, on a CPU, be competitive with the FSMI or even better. And then afterwards, I don't have time to talk about it, we did some specialized hardware to speed up FCMI, and that gives you another several orders of magnitude speed up. So the high level message, again, this is just for MI, is that really there's a lot of gains to be had by, thinking both at the algorithm and then hardware standpoint in terms of really jointly optimizing them for speed and energy. And you can do this through multiple iterations. And this can result in orders of magnitude speed up. Okay, and of course, this allows us to do mutual information for the entire map in real time for the first time. Okay, so two quick things before I end. I think I'm towards the end. So the one thing is, we talked a lot about computation, but we also want to talk about the interplay between computation and actuation, and computation and sensing. So very briefly, in terms of computation actuation, if we're thinking about these very kind of low power, low energy robots where, actuation is cheap, you might want to rethink the balance between the two of these. So one typical task that relates to actuation energy is motion planning, right? So I don't have to explain too much to you guys, because from start to goal without, with finding an obstacle-free path. And then, as we mentioned, there's a whole range of robots that actually the energy cost to actuate is on the same order of that to compute. So then what we really want to do is strike a balance between the two. So in the past, I think historically, what folks would do is that you would just do as much computation as you can to find the absolute shortest path, and then you can minimize the actuation power. That's traditionally the way you would do it. What we're advocating here is that you shouldn't do that. You should balance the two, because net what you want is your overall system to be very energy efficient, right? So this was realized in an approach called compute energy included motion planning, or CEIMP. And the idea is this is a framework that allows you to kind of estimate whether or not I should continue computing. What is the probability that I will find a shorter path given what I already know, or should I stop now? Because I also have to figure out how much energy I would be spending if I keep on computing, right? So in this particular case, this is the time. So you can see that, at the beginning, when you're trying to find a shorter path, the actuation energy goes down and the computational energy goes up. And ideally, you would recognize a place to stop over here. Otherwise, you're not actually saving any more in terms of actuation energy. It's diminishing returns, but you're still spending a lot in terms of computational energy. So the high level message here is kind of like, don't think too hard, right? Like, don't spend more energy planning where you should go than just to go there. Sometimes you just start walking, right? And then lastly, we used monocular depth estimation, but you could also use time of flight depth estimation. We know that that's also very widely used. The reason why it's an issue is that if you do active sensing for that, you need to send out like some, pulse to figure out how far away things are. That's going to be very expensive. And so in a similar type of approach, what we can do is leverage the temporal correlation to minimize how often we turn on this depth sensor itself. So you can imagine you only turn it on for that like first image, and then based on the temporal correlation, you can estimate what the depths will be from the RGB image that you get, which is pretty cheap, of what the depths would be for the other images itself. And so by doing this, you can run this again on a very cheap, low power computer and still get real-time VGA depth estimation. And of course, what matters is also the quality. So, on the TUM data set, you can see the mean relative error is 0.7% when you're only enabling your depth, your laser at 11%, basically 1 out of 9 frames. Okay, so what is the high level? We covered a lot of things. What is the key takeaway or themes of what we discussed today? First is that, I hope you all agree that efficient computing is really critical for advancing the progress of autonomy, particularly at the small scales, but we also know it has implication even large scale on things like carbon footprint. So we really need to think about enabling efficient computing. In order to meet the compute demands in terms of both the power, energy, and speed, we would advocate redesign of the hardware from the ground up and really kind of focusing on data movement. That's really what is contributing to energy consumption and latency. And a way to do this is kind of doing the co-design of both the algorithms and the hardware itself, right? So kind of this joint optimization of both. And sometimes if you iterate multiple times, you can get orders of magnitude savings. And this gives exciting opportunities for the future of robotics in the sense of in the past, I think we often focus, if you're looking from the algorithm side, you want to optimize your code so it runs really quickly on CPUs and GPUs. But what if now you could say someone's actually going to design you any type of computing hardware? That really opens up the design space in terms of how you would want to design your algorithms to make them efficient. Of course, then all this work is done by many students. So would not be possible without them. And in collaboration with Joel Emmer, that's more on the DNN hardware side of things. And then Sartesh Karaman on all these autonomy and navigation applications, and of course, all of our sponsors. Again, I covered a lot of material today. I would encourage you to visit the Lean website if you really want to learn about the autonomy and navigation specific applications. But then also in the context of efficient DNN processing, we've also done a lot of work on this with Joel Emmer. So we actually have, in addition to those overview papers, we have books and tutorials on this. So we actually use this book in our own class that we teach at MIT. So if you're interested in that particular topic, really looking from a computing standpoint, I would encourage you to take a look at that. And I think that's basically it. So with that, I'm happy to take any questions.
Okay, thank you very much. As a reminder, participants that are on Zoom can write their questions in the Q&A section, and we will read them live for Vivienne to answer. I would like to start with my question, is that on the flip side of improved hardware architecture on the energy side, is that it enables us to do things that were not possible before. There was a very famous paper by Professor Konidaris at Duke about motion planning on a chip. So I would like to ask you, what are your takes, besides the low power architectures, are there robotics architectures that are going to be enabled by specialized hardware architectures in robotics?
Yeah, so I think the work from, it was Duke for doing like motion plan is very exciting because it just showcases that by, using specialized hardware for the motion planning itself. And there they're using, I believe they're using FPGAs. And even then you're getting a huge amount of speed up. I think what I would say is there's a couple of things. I think, first of all, anything where you're limited, any robotics application or even like AR, VR applications where you're limited by compute, either from an energy and or I should say from a speed point of view, using specialized hardware for that can really open up a huge space. So for example, looking at that mutual information work that we did, I think traditionally people thought that's a great approach because it has theoretical guarantees, but the computation of that is just ridiculously high. I would not do that in practice. But showing that you can redesign the algorithm and the hardware together can then make it possible to, in that case of the work, you have now mutual information for the entire map in real time. And the question is, what can you do with that information? Can you now enable new applications by using that? There's also this whole kind of class of low energy robotics, like, those robots that take very little energy to actuate. In the past, they didn't have much autonomy to them, but now by adding these types of functionalities to them, you could potentially make them autonomous. And some of these applications are really exciting, right? So for things like, let me go back to that slide. I guess I should say all of them are exciting, but some of the things like for like deep sea exploration and stuff like that, you can imagine if you're able to, make these, sea gliders more autonomous and they can explore the sea much more efficiently, then you can collect a lot more information, which would be very helpful in terms of advancing science and having a better understanding of what's going on down there. Similar to kind of deep space exploration too, right? You can imagine as you launch these satellites, if you want to have some autonomy of them, so whether to like automatically position themselves and so on, I think there's a lot of exciting opportunities there as well. Basically, it's like trying to reduce the cost of adding some autonomy to these wide range of applications. What does that enable? I hope a lot of exciting new things.
Thank you very much.
All right, we will take some questions from the audience.
Thank you for such a fascinating talk. I have I did not follow how the mutual information work would be used if the map were being built online. Does it also work or no?
If the map was being built online, do you mean if the map was like
For SLAM.
dynamic?
For SLAM.
Or SLAM. I think, as long as, so basically what the mutual information does is it takes in an occupancy map, right? And then given, knowing what your depth sensor is, can it actually predict what the mutual information inform how you actually can go to a given location? If that map, given that you can compute the MI in real time, if the map changes, you can quickly recompute it again and again. So that can help inform, like, given if you're going to update the map after you've gone to a certain place, right? You can update the map very quickly and then compute the mutual information for the entire map. You don't have to, for example, just compute locally in terms of, oh, if I go in this one location or one location, will I get new information? You can just see the entire map overall.
So
you
the
can
access patterns remain similar?
Yeah, so the access patterns only depend really on the fact that you're doing a diagonal access pattern on that occupant. So you're basically, if your depth sensing is radial, right? And then the number of rays that you have, right? That basically you saw, like, in terms of the banking, it actually is primarily having to do with the fact that it's radial. I should say that some more recent work that we did was like actually moving from the diagonal banking pattern to like a Latin square banking pattern. That's a little bit more efficient, particularly for the arbiter. But really the question there, which was an interesting problem in architecture, we haven't looked at this before, which is that if you have a diagonal, if you have a grid that you're trying to store in memory, you're trying to access it from a diagonal point of view, how do you bank that memory?
Mm-hmm. Yeah.
So as long as that holds, then you could use it. Yeah.
Thanks.
Thank you.
I had another question regarding Navion. In terms of performance, how did the system perform indoors? What was the input frame rate for the camera? If you could repeat. And
yes.
Were there like any cases where the system broke, or any assumptions that were not hold and made the system's performance worse?
Yeah, so we tested, I actually don't have the slide here, but we tested the accuracy of it in terms of just like how accurate it was on the UROC data set. So it's all in the JSSC paper that goes with this. So from the algorithm standpoint, that's basically what we tested on. In terms of the camera rate, it varies, and this, I'm trying to remember, this varies. I think it does vary. The reason it varies is it varies across the data set, having to do with, I think part of it is the front end and part of it is the back end that changes based on the features that extracting, and then basically the size of the factor graph that's being optimized. So the number of features that has to track and the optimization in the back end. So that's why there's that variation, but these are all measured. So the Navion chip was evaluated on the UROC data set. So whatever's there, that's what this was evaluated on.
Thank you.
That a question? Yeah.
Thank you so much. If there are no other questions, we can conclude. Thanks. Thanks, speaker, again.
Thank you very much.
Thank you.
So as closing remarks, this is the last graph seminar of the semester. There is one exception, however. We have a special summer seminar on Friday, June 9th, 10:30 a.m. By Pauline Pounds from the University of Queensland. Thank you so much for joining.
Thank you.